Hello friends and my dear students. In the last session we have discussed about designing of shaft. So today we are going to discuss about the bolt design under variable stresses, where first of all we have to understand that bolt of uniform strength, how it will look like, or what are the different properties of this particular bolts. So basically bolts are subjected to shock and impact loads in certain applications. The bolts of cylinder heads of internal IC engine or bolts of connecting rod are the example of such application. Means they used to encounter shock and impact load under various applications. So in such applications, resilience of bolts is important criteria. What is resilience? Basically resilience is defined as ability of the material to absorb energy when deformed elastically and to release this energy when unloaded. Okay, so this is also called as spring property. Okay, so resilient bolt absorbs energy within the elastic range and without any permanent deformation release this energy when unloaded. Okay, so this is called as spring property of bolt. Sometime it may be asked in your competitive exams or maybe in your university exam that what do you understand by the spring property of bolt, then you can explain this particular content. Okay, so a resilient bolt absorbs shocks, vibrations like leaf spring of vehicle, or in other words, bolts act like a spring whenever it is required or under uniform strength. Now, the major diameter of the thread as well as the diameter of shank is D. The core diameter of threads is depicted by DC. When this bolt is subjected to tensile force, there are two distinct regions of stresses. Means there are two different kinds of stresses which are going to apply. First is the diameter DC is less than the shank diameter. So the energy absorbed by each unit volume of the bolt is proportional to the square of the stress. So hence large part of the energy is absorbed in threaded portion. Means most of the energy of the bolt has been absorbed in the threaded portion of bolt instead of head. So next is the diameter of the shank is more than the core diameter of threaded portion. So therefore no stress concentration is there in the shank. So when bolt is subjected to the tensile force, the stress in the shank portion is less than the stress in the threaded portion. That's why the energy absorbed in the shank, which is proportional to the square of the stress, is less than the energy absorbed in the threaded portion. So these are the two different criteria which you can see where stresses are going to apply according to the size or diameter at different sections of the bolt. Now there are two methods for increasing the shock absorbing capacity, or you can say the resilience you can increase with the help of these two criteria. Either reduce the shank diameter to the core diameter of the threads, okay, or increase the length of the shank portion of the bolt. If you will adopt any one of that, then you can increase the resilience of the shaft somehow. Okay, now let's jump to the calculation part of the bolt, where you can see that how you can calculate or how you can design the bolt or bolted joints. As you can see in the picture, that capital D is depicted, DC is depicted, H height of the head is depicted in the picture. So now you can calculate the value of your maximum tensile stress at the cross section, okay, which is called as sigma T, which is equals to P, which is the load applied on this, divided by pi by 4 DC square. Then you can also substitute or use sigma T as equals to S by T, which is the ultimate tensile strength divided by factor of safety. This is depends on your material, so you can also calculate this value with the help of this, and you can equate this sigma T is equals to S by T by Fs over here. Then you will get this value as P is equals to pi by 4 DC square S by T by Fs. Similarly, if S by T is not given, then you can also use this particular formula for the shearing area, or you can say shear area, and this shear area is equals to pi DC H, where H is the height of nut. Then you can equate, then you will get this value, and if you will equate equation A and equation B, then you can say that H is equals to 0.5 times of DC. So for, and assuming DC is equals to 0.8 D, H you can say as 0.4 D. Means for the standard coarse thread, the threads are equally strong in failure by shear and failure of by tension if the height of the nut, okay, if the height of the nut is approximately 0.4 times of the nominal diameter. Okay, similarly, if you will also correct this relationship for the ISO metric square threads, then DC will be equals to D minus 1.22687 P, and DC can be depicted as 0.8 D. Let's see one numerical for the same. As you can see in the picture, you have to calculate the size of the bolt, okay, and they have just adopted two formula. Sigma T is equals to S by T by Fs. They have calculated sigma T, which is permissible stress, and as you know that sigma T formula for the bolt calculation is P divided by pi by 4 DC square. Keep the value sigma T here. You know the value of P, which is load. You know you have to calculate the diameter DC. You can calculate it easily, which is the D, and after that you can calculate the value of D, which is the standard size of the bolt, okay. So with the help of this simple formula, you can design any kind of bolt or any kind of calculation related to the bolt design, okay. Most of the things are given, and these are very easy sort of numericals, I will say, in your particular chapters related to the bolt design, okay. You can go through it and try to solve this numerical at your home, and do comment in the video comment box if you have any kind of doubt, and stay tuned with our Engineering College Banswara YouTube channel for more such updates about different branches of engineering like computer science, CSE, mechanical, electrical and civil. Thank you so much, and do subscribe Engineering College Banswara YouTube channel for more such update about such content related to the various curriculum of Rajasthan Technical Universities of different branches of engineering. Thank you so much.